Okay, so we ended yesterday at the point of this saying that there were we can have the models can be replica symmetric or replica symmetry breaking, and so the first thing I want to discuss this morning is the different phase transitions these models go through, and essentially how you derive the thresholds for where they occur. And so this will is at least conjectured to apply to random colorings, the hardcore model, and sort of maximal independent sets, random k-sat, nodal equal sat, and various other models as well. Okay, so if you've been to talks with me or my collaborators or other people working in the field, you've seen this sort of ink block looking picture before, I'm sure. But so I want to in detail describe how we work out where these transitions occur and why we expect them there. So when we have a low density of constraints, sort of a graph with a small number of edges, the prediction is that you should only really have a single component of the solutions with almost all of the solutions. But then there's a transition, a clustering or shattering transition, where the space of solutions splits into exponentially many clusters, each with an exponentially small fraction of the total number of solutions, and all sort of well separated from each other. This seems to be the point at which, like from an algorithmic point of view, the problem starts becoming hard. And you can imagine sort of like a local search algorithm for finding a solution to such a problem won't do well if, or might not do well if the solutions are all sort of very clustered and far apart, and particularly if there are lots of sort of almost solutions that aren't close to a real solution, which is what happens. Okay. But still, in this regime, it's replica symmetric, and the reason for that is essentially all of the clusters are small. If you pick a couple of random solutions, they'll be very unlikely to lie in the same cluster. And if you and so for something like the random colorings, the typical number of solutions will still be close to the expected value in this regime. Okay. The next transition is the condensation transition. So yeah.
Can you remind what you mean by cluster here?
Oh, okay, that's good. So so there's a couple of ways of thinking of clusters. One is we could think of two solutions as being, say, adjacent if they just differ in one of the variables, or maybe a small number of variables. So you could think of clusters as being connected components of solutions with that notion of adjacency. And so in a sense that would be like saying, if I want to go from one solution to another, just changing one variable at a time, can you do that? That's not going to be a very tractable sort of definition for clusters, though. And on Monday, sort of gave another description of how you might imagine for a cluster, which is that it should correspond to a fixed point of the belief propagation equation. So, so we have our graph, and on every half edge between u and v, there's a message m from u to v, which indicates the probability that u thinks that, so this will be a probability distribution in colorings over the set of colors, in general over the set of possibilities for u. And what it's meant to represent is what U thinks its color should be if it forgets that it's connected to V. And so a way of encoding the cluster would be to have a set of these messages on every edge satisfying a sort of consistency equation, which is that if you take all the other incoming messages into U, that the message from U to V will be given by some function of the incoming messages into U. And this function is essentially just the function. It will depend on the spin system, but it's essentially just the function of if you have trees rooted at vertices U1 to UD, and they have marginals M of U1 up to M of UD, and then you add in a new vertex, U, connect them up, then you can calculate the marginal probability at the root. That's the Bully propagation equation. So it's really about recursively analyzing marginal probabilities in trees. So you know the marginal probabilities on the children. What's the marginal probability at the root? And we ask that that we have such probabilities on every directed edge in the graph, and that they need to all be consistent. And when we're in this sort of clustered regime, at least if we're at zero temperature, so in principle these probability distributions could be any distribution on the simplex, but actually for something like colorings, most of them will be point masses. Most of the time it will be, you could generate it by just starting with a coloring, and most of the time, if at some vertex here it's blue, most of the messages coming out of it will just be saying that I'm blue with probability 1. And what that corresponds to is that within these clusters are very rigid. Within the cluster, most of the variables are always the same, always take the same value. So they know I'm always going to be blue or I'm always going to be red. There'll be a small fraction of the vertices where they could take different values, and so if you had a vertex here, maybe it's blue but all of its neighbors are red, then this vertex could either be blue or green within that cluster, even if these are always fixed to red. So but in a sense, the clusters that we'll be interested in will be very rigid, and encoding, and the idea is we want to encode them by, so we could think of them as just connected components, what you can get from, which colorings you can get from one to another, but it's better to think of them in terms of sort of this combinatorial description of messages being passed along directed edges.
Am I correct in saying that you are sort of implicitly saying that in the case of the colorings, either you have one RSV, and if it's not one RSV, it will be infinite RSV, or that you never really get 2 or 3 RSV because of this sort of tree structure?
So we certainly don't know that that's the case. I think for colorings, the prediction is that whenever you have at least whenever you have at least 4 colors it should be 1 RSB. For 3, I think full RSB, but I'm not sure even at the level of I think that's mainly just because it's not expected to be like 2 RSB or 7 RSB, but I don't think there's a sort of, yeah, certainly not a proof. You can, okay. What is possible to show is that, so there's a 1 RSB prediction, and for, say, the number of colors that you have, the number of colorings, and one can show that that's a sort of not the right thing, and that it's an overestimate of it. Yeah. Okay, good. So that, okay. So in this condensed regime, we expect there's still exponentially many clusters of solutions, but there are big ones, ones that have a constant fraction of the total number of solutions. And so if you look within a cluster, most of the variables are all just fixed, and there's just a sort of small subcritical sets of say vertices which can have different colors, and so it behaves a lot like a product measure. And so if you looked at the colorings within a cluster and looked at 2 random vertices, the joint distribution would look like a product measure. But because the mass is supported on like a small number of clusters, you know, a mixture of product measures is not a product measure usually. So so the distribution in this phase will be more complicated. The sizes of the clusters there's a prediction that they're a Poisson-Dirichlet distribution with some particular constant. I think this is not known in any of these CSPs. Oh. And of course the final transition is the sort of satisfiability one, the point at which we have no more solutions. I've drawn the sort of 1 RSB out a bit further because you can imagine saying, okay, at some point it's not possible to satisfy all of the constraints, but you could look at what is the solution that satisfies the most number of constraints, and the sort of 1 RSB formalism is expected to apply sort of in that regime as well, out to a certain point, sort of some higher density of constraints, but sort of somewhere, you know, off here, there's another transition, and it's supposed to become full RSB at that point. But say in the case of, I'm not sure where the transition should be for random colorings, but for the random K-SAT model, satisfiability is when the density of constraints is about 2 to the K, and this sort of later on transition occurs at about 4 to the K. So, okay. So that's sort of a qualitative description of each of these transitions, but there are also predictions for where they all occur. And so to describe this, well, first of all, I want to do it in a sort of slightly simpler case where we're dealing with models on random regular graphs, and that just means that it's easier to talk about expectations of quantities rather than the replica symmetric solution, which is slightly different. But and so imagine that there existed exponents capital sigma, which tell us how many clusters we have of a different size. So the number of clusters of size e to the ns, so that have e to the ns number of solutions in them. Suppose that we know that that's e to the n sigma of s, and that such an exponent existed. Then we could calculate the expected partition function by just summing over all the different cluster sizes. And because this is on sort of a sum of exponentials, the biggest contribution is going to come from the s that gives us the biggest exponent, so the biggest value of s plus sigma of s. So you want to maximize this quantity, and this happens in different ways as the degree distribution changes. So in the clustering, so if this is sigma, then maximizing s plus sigma of s is just the point at which the derivative is -1. And in the clustered regime, the picture looks like this, with a sort of tangent point above the x-axis. The condensation threshold will be the point at which the tangent point lies on the x-axis. Then in the condensation regime, it's strictly below the x-axis. The satisfiability threshold should be the last point at which you have a non-negative value of sigma, so the last time you have clusters of colorings of any size, and then when it's unsatisfiable, it's always negative. Okay. So how does this explain why you get a different behavior in the condensation regime? Well, the biggest contribution to the expected value is coming from clusters of this size, but they have a negative value of sigma, so it means that they're exponentially unlikely to appear. So the expected value is dominated by very atypical clusters of solutions that you don't expect to see. So what should you expect for the typical number of solutions? You should look at the biggest cluster size that you actually expect to occur in a typical instance, which will just be the largest root of sigma, the largest non-negative value. And so that's the prediction for the typical number of clusters. And of course, sigma is 0 at the root, so it means that you expect to see e to the 0, or just order 1 number of solutions, and that's why you expect that the mass here is dominated by just a constant number of clusters. If you're willing to sort of further interpret sigma as not just the expected number of clusters, but really the intensity of a Poisson process, that would lead you to the prediction that the cluster sizes have a Poisson-Dirichlet distribution. And the parameter would depend on the angle at this, the derivative at the root. Okay, so just to summarize all the predictions, the condensation threshold is the point at which this tangent point lies on the x-axis. Is known in a couple of cases. Random Q colorings of Erdős-Renyi random graphs when Q is large, and also for the regular K not all equal sat model when K is large. So, and here regular means every variable, so it's like a random regular version of K-sat. So every variable appears in the same number of clauses, and somehow that makes the problem more homogeneous, and so as you'll see, there's definitely more results in the regular cases of these models. Inside the condensation regime, you also get a prediction for the typical number of colorings or solutions, which is just the value of this root. And the only regime in which we know this, or the only model in which we know this, is for the regular K not all equal sat model with K large. The satisfiability threshold we know for more cases, also for the size of the largest independent set of a random D-regular graph when D is large, and regular not all equal sat, a regular version of sat, and then the only model in which we know it for where the graphs are not regular is the k-sat problem when k is large. And so it's just the point at which, and so satisfiability is just the last sort of largest alpha or d at which you have a non-negative value of sigma. So with all these results, it's always large K, large D, large Q for colorings. The reason for this is mostly technical. When the degrees of the graph are big, they're just more concentrated, and lots of quantities become much more concentrated and easier to deal with. On the other hand, some of these results are not true if you have small enough values of the parameter. So for the largest independent set, the proof was for large values of d, but actually when d is smaller than 20, the 1 RSB predictions are not supposed to hold. It should be it's supposed to be full RSB below for 19 and smaller. On the other hand, for the random k-sat model, for all k greater than or equal to 3, this the 1 RSV predictions should hold. Okay. But now, I haven't really made predictions yet because this was all in terms of some sigma that we don't know if it exists, and more importantly, we don't actually know its value. So how do you calculate sigma, at least heuristically? And here, having the view of a cluster as a collection of messages is really important. So, okay, so M here, if you remember from last time, was a collection of messages that satisfy the belief propagation equations, and we can view this as a spin system by itself, spin system and constraint satisfaction problem in its own right. The constraints are just that on every edge, the belief propagation equations are satisfied. Okay, and then W of M was just the number of solutions within that cluster of solutions, and at least if you believe that it's like a tree, you can use a formula for the number of solutions in terms of a product of local quantities. Okay, and so we'll look at the distribution of these clusters weighted by the number of solutions, but also to the power of lambda. And you can just incorporate this lambda into the weights of the problem. Okay, and so why would you want to do this? Well, if you look at the expected value of this partition function, what's the contribution to it from clusters of size s? It will be e to the n s lambda times e to the n sigma of s. And so if you take the log and 1 over n, the contribution for clusters of size s will be like s lambda plus sigma of s. And then, okay, and it will be dominated by the sort of biggest contribution, so just the maximum of this value. And this is just the Legendre transform of sigma. So if you can compute moments of this partition function, you can compute the Legendre transform of sigma of s. Or another way of thinking of that is you choose a value of lambda that sort of tunes the weight of the clusters so that the typical cluster size under this measure is of size e to the ns, and then sigma, the sort of number of them will be like the log partition function for that lambda minus the typical contribution per cluster. Okay. So if you can compute moments for this fairly complicated spin system, then you can work out sigma, and that gives you all the set of predictions that you want. And say in the case of the satisfiability threshold, it's simpler because for that we just wanted to know what the maximum of sigma was, and that corresponds to lambda equals 0, which corresponds to just looking at unweighted clusters. And so that simplifies things a great deal, and that's one reason why there's more results for the satisfiability threshold than the other problems. You don't need to start talking about the weight of clusters or weighting them by how many solutions there are. Okay, so then the next okay, so this leaves us with the problem of we have a random graph, and we have some sort of a spin system on it, and it's got some set of weights. How do you work out the moments of its partition function? Okay, and it turns out that there's sort of a nice way of, or there's a nice general approach to doing this. So just a general setup. We have say a random deregular graph with some set of weights. And for a configuration, we can talk about the edge empirical distribution, which will just be how many edges you have with state x on one end and state y on the other. So it's, and the vertex empirical distribution would just be the same for vertices, how many vertices are in each state. And it turns out it's convenient to it's easier to calculate the expected number of solutions once you fix the edge empirical distribution. Okay, and so okay, how do you compute anything with a random deregular graph? Well, the simple way to do it is in terms of the configuration model, which if you haven't seen is a nice way of constructing these random graphs. So you just you take your n vertices and say we want it to be deregular, so we have d sort of outgoing edges for each of them, and then we just take a perfect matching of these, and that tells us what the edges between each of the vertices are. Okay, and this is your graph, except for the fact that you might not get a graph because some things could go wrong. You could have, well, for this vertex, one of its half edges is connected to the other, and you would get a self loop. Another possibility is that you have more than one edge between a pair of vertices, and neither of those things are allowed in a simple graph. Okay, but if you condition on the event that you get a simple graph out of this procedure, then you get a uniform one, just by symmetry. Okay, so what's the chance that things go wrong? Well, it's not hard to show that the probability that you get a simple graph out of this construction converges to a constant, which is bounded away from 0. And the constant just depends on the d, the degree. So, and so with a constant probability, you're getting just a uniformly chosen simple graph. So, so it's sort of okay to work in this model instead. Okay, so how can we work out the moments of a spin system on the random graph? Well, we want to count what's the expected number of configurations that have a particular edge empirical distribution h. So imagine we have h. That will also tell us the vertex empirical distribution. So we know how to assign the spins to the vertices, how many greens and blues and reds we have. We also know how many green vertices need to be attached to a blue vertex and to red ones and so on. And so we can assign those at random given the proportions that we need. And then we just choose a matching that's compatible with it. So in this case, a green vertex that needs to be matched to a blue one should be paired with a blue vertex that needs to be matched to a green one. And so all of these terms are just, you can write out in terms of binomial coefficients for the number of ways of assigning the vertices, the number of ways of assigning colors to the half edges, and then the number of ways of doing the matching. Okay? So you get a formula, you can, there's lots of factorials, so you can just apply Stirling's formula lots of times, sort of expand everything out, and you get the following formula. So the expected, well, if there were no weights in the spin system, then the number of ways of, or the expected number of configurations with edge empirical distribution H would just be this term here. There's something in terms of the entropy of H, but then you also need to subtract off something in terms of the entropy of the vertex empirical distribution. And then, because we're talking about weighted spin systems with weights psi and bar psi, then we also get these terms as well. Okay, and so this is the contribution to the partition function. Just looking at configurations with this particular empirical distribution. And so then we want to know, okay, which empirical distributions give the biggest contribution. And okay, so we want to maximize, so phi of h will be this function, and we want to maximize it, but it's potentially a quite high-dimensional optimization problem, and it's non-convex, like we saw for the second moment method for the random colorings. You get multiple peaks. So so how do you do this optimization? So it turns out you can characterize the stationary points of this function phi in terms of fixed points of the belief propagation equation. So something is a stationary point if and only if there exists some function, some distribution m such that m equals bp of m, and that h is of this form. So the probability of seeing x and x prime on an edge is mx prime times psi of xx prime. So how to interpret this? Well, imagine you had two trees, and the marginal probability here was m, the marginal probability here was m. If I add an edge between them, there's just a quick calculation shows that the marginal probability of these ones will be proportional to this, because that's essentially what these weights in a spin system do. Okay. So and so what it's saying is that essentially on every edge in the graph, the messages should correspond to m. Okay. So so it sort of reduces the problem to finding what fixed points you have of these equations, and somehow this is simpler than the overall optimization problem. So the proof, well, one proof is just you can do it by calculus, and it's actually not that difficult. I'm going to tell you a different proof that involves a sort of resampling argument of the graph and the configuration. Okay, so imagine we have a random deregular graph on n vertices, and we're going to choose epsilon n of them as a set W, and let's say we've chosen them at random, but in such a way that they're not next to each other. Okay, so we have W, we have its neighbors, and we're looking at a graph with a configuration on it. So you think of a graph with a coloring, and the procedure is the resampling is going to, okay, and imagine it was uniformly chosen. So the empirical distribution should be one of the maximizers of phi. And so we want to show that that's going to be of this form that's given by a fixed point of the BP equations. Okay, so the resampling will be, we'll just remove all the edges of W and forget about their spins. And then resample them according to the weights of the model. Okay. So when we do this resampling, all that was really important was to remember what the empirical distribution was on the neighbors. So they stayed, so the coloring in all of the rest of the graph stayed fixed, and then just the coloring that we had on the neighbors of, original neighbors of W was what was important. So we're essentially sampling these trees, conditional on the leaves having this empirical distribution. Okay. So and this is another way of saying it. So it's like looking at a spin system. So the law after we resample, which of course has to be the same as the law before we resample. This will be an resampling is exchangeable. Okay, is like taking a collection of epsilon n d stars, or just graphs of depth 1, putting on sort of weights of them, and then conditioning that when we do that, the distribution we get on the leaves will be given by the original empirical distribution there. Okay, but what you can say is, if I did the same thing, but also put some external field or weight, extra weight on the leaves, that wouldn't change this distribution because because of how we're conditioning it, it will mean that every configuration will get the same weight. Okay, so we can choose a weight such that this conditioning is likely to happen, or at least it's, rather than a large deviation event, it's like a local central limit theorem event. It happens such that the expected distribution on the leaves is given by what we're aiming for, and so then the probability that we see that distribution will be maybe only polynomially small. So then we can think of the distribution here as just an IID distribution over these trees with these weights, and the edge empirical distribution will be concentrated, and you can work out what is the edge empirical distribution on one of these edges, and well, adding in these weights m was like adding messages of m on each of these edges. So all of the upward directed edges have message m, and then the downward messages will be the belief propagation function applied to m. So if you look at the joint distribution on an edge starting from one of the roots to one of the leaves, it will be proportional to psi, the weight, BP m of x, and m of x prime. That's the probability that you see x here and x prime here. Okay, so if m were not equal to BP of m, you'd have a different distribution at the root and the leaves. But we just chose okay, how do we construct everything? We just originally, we just chose vertices at random and looked at their spins and their neighbors. So, we could have equally, and so if you do it in that way, the distribution of the roots and the leaves must be symmetric just by symmetry. Because we were equally likely to choose this vertex and have this as a neighbor as choosing this vertex and having that one as a neighbor. So the distribution must be symmetric, and the only way that can happen is if the BP m is a fixed point of the BP equations. Okay. So, so that reduces the problem of calculating moments to the problem of solving these BP equations. Okay, so the next thing I want to address now is to sort of apply this in the case of looking for the largest independent set on a random deregular graph. Sort of a very natural combinatorial question. And okay, so just if you remember from last time, an independent set is just a subset of the vertices that such that there's no edges in the induced graph. So if you have a coloring, the set of vertices of one color has to be an independent set. Okay, and we can ask, what's the biggest size of an independent set that you can find in your random graph? Okay, so it's not a priori clear that there's even a limiting density for this. But first of all, I want to tell you what I think is a very beautiful, or at least very cute argument that says that essentially there's superadditivity for the size of the largest, or at least the expected value of the largest independent set, and so that the density must converge. And this is the interpolation method. It came originally from the study of spin glasses, work of Guerra, and was really important in the sort of eventual proof of the Parisi formula and for that. It can be. It was then applied by Franz and Leone and Panchenko-Talleyrand in the case of sparse models, like KSAT and so on. But the formulation I'm going to tell you and the application to independent sets is really just an extension of this, but it was given by Baiati, Germanic, and Totali. And they also extended it to the case of regular graphs. And the idea will be to construct a sort of interpolation between two disjoint graphs and a bigger graph that is sort of the combination of the two. And so one way of doing this is in terms of the stochastic block model. So this is a model on it's sort of an inhomogeneous model of random graphs, and it's really big in statistics these days. The idea is you have your random graph and you have two, well, okay, in the simplest version you have two sets of vertices. I'll call them V plus and V minus, each with n over 2 vertices. You can imagine like people from Cambridge and people from Oxford, and that you're more likely to be friends with people in your own university, but you also know a few people at the other place as well. So you have edge density A over n within the group and B over n to the other one. Okay, and the statistics question then is: suppose I don't tell you which one is in which group. Can you work out? Can you work that out without the labels? And actually, some of the theory in for spin glasses and random constraint satisfaction problems tells you about the different sort of statistical thresholds for when you can do statistical inference in these models. But that's a different story. So we're going to use this to interpolate between one Erdős-Renyi random graph and two. So imagine, let A and B vary with t. So A will be d plus t times d, and B will be d minus t times d. So when t equals 0, you just get the standard Erdős-Renyi random graph with average degree d. When t equals 1, it will be A will be 2d and B will be 0, and that will correspond to no edges between the groups. And you have two Erdős-Renyi random graphs, each with n over 2 vertices, but still with average degree d. So it's so this will be sort of a way of comparing graphs with half the size to half of n to n. Okay, and of course we could have different splits of the sizes as well. But okay, and we want to see how the expected size of the largest independent set varies as we change the parameter t. So imagine you have a graph and you add in an edge and you want to ask, does that change the size of the maximal independent set? And of course it can only make it smaller. And when does it make it smaller? Well, let's let S of G be all of the vertices that are in every maximal independent set of the graph. It will only decrease if the edge joins two of the vertices in S. If one of the endpoints wasn't in S, that would mean that we could take an independent set that sort of that also agreed with for which that edge wasn't a problem. Okay, so if we differentiate the size of the largest independent set in say A, that's like asking what happens when we, so there's a so if you think of the infinitesimal change, it's like you have some chance of adding in edges between vertices. And so what's the chance that you add in an edge that goes between two of the vertices in S? Well, because we're only changing A, these are the edges within the groups. It will have to be an edge between either two vertices in V plus or two vertices in V minus. This is sort of the number of them. And okay, if we differentiated in B, you'd need one vertex that was in S and V plus and another one in V minus. And if we sort of put those together and look at the expected change as we parameterize, as we differentiate in T of this interpolation we had, it's sort of the difference of these two terms, and what you get is essentially the difference in the density of S in the two halves of the graph squared, plus a term that's presumably smaller order. This will be sort of a small enough term to ignore. And this part is always negative. So what that means, so if we ignore this part, it would mean that the expected independent, well, okay, the expected size of the biggest independent set on the Erdős-Renyi random graph with n vertices is more than double the expected size when you have n over 2 vertices, with some sort of order 1 error coming from sort of this bit, which is, this is coming from the fact that this, like, m choose 2 is not quite m squared over 2. Okay, but it's enough to apply a sort of argument of superadditivity and say that, the density of the largest independent set converges. Okay, so, and this was an open problem of one of David Aldous' favorite problems listed on his website for a long time. Okay, so of course, if you have an argument about superadditivity, it tells you that there's a limit, but it doesn't tell you doesn't necessarily tell you anything about what the limit is. But there's another version of this argument which gives you the limit, but also gives you a way of getting bounds as well. And I'll also tell you it in the context of the random regular graph. So this one is Baiati, also Baiati, Gamane, Totali. Oh, and I should mention that this sort of miracle wasn't just for maximal independent sets. It applies. We could have done the same thing with looking at the log partition function and how that changed as a function as we did the interpolation formula for sort of positive temperature versions of the partition function. So you imagine for a random constraint satisfaction problem, we no longer disallow solutions that have that violate some of the constraints. We just penalize them according to e to the minus beta times the number of constraints that are violated. Okay, and you could imagine that for large values of beta, this should be close to just the set of the solutions, just the true solutions. Okay, and so this applies for some models, the antiferromagnetic easing model or Potts models, the hardcore model for independent sets, and finite temperature versions of random k-sat and novel equal sat. It doesn't apply in general for spin systems. There's just some equation that has to, or inequality that has to hold for the interpolation method to work. And so, for instance, for the ferromagnetic easing model, it doesn't. You can't use this. It also doesn't apply at 0 temperatures when beta equals infinity and you're just looking at sort of the solutions that don't violate any of the constraints. Okay, partly because there could be 0 solutions and you can't look at log of 0, but and I mean, well, no one has found a method for getting this to work at 0 temperatures, and that's unfortunate, because if you knew this, you would automatically get the existence of the satisfiability thresholds, if not but not with the locations, but still that they exist. So it's kind of tantalizingly close to at least being able to show that you have satisfiability thresholds for all these models, but it doesn't work at 0 temperature, which, at least for constraint satisfaction problems, is the most interesting case. But for something like the antiferromagnetic easing model, it tells you that the normalized log partition function converges, for instance. Okay, so this is interpolation with sort of regular graphs. So imagine we have a graph M, where M is, say, much bigger than n, and so a random deregular graph with m vertices. And so imagine, and then we just chose a small number, we chose n of those vertices. So imagine below W there's actually some big graph here that I'm not showing. But I want to keep it sort of, I don't want to exactly specify what's happening down here for reasons that we'll see. So we could do the interpolation as follows. First of all, we just delete n to the 2/3 number of edges. This is just somewhere between, sort of something between root n and little o of n. And then, so that's not part of the interpolation. This will just give us some error term. And then sequentially, we pick one of the original edges, and with probability half, either add in an edge between vertices of U or between vertices of W. So, and keep going like this until there's none of the original edges left. We need to throw in a few more edges because we deleted some just at the beginning. And so what we'll get is, and we'll do it in such a way that we have a deregular graph on U, and each of the vertices of W have exactly one edge, so a matching of those. Okay, so what we're left with in the end is a random deregular graph on n vertices of U, and this matching of edges here of W. And if W were chosen in a sort of, if this was originally coming from an m-vertex random deregular graph, then W would sort of form part of now a random graph with m minus n vertices. So this would be an interpolation that splits the graph from m vertices into m minus n and n. Okay, and okay, so we could do this with the hardcore model. We could also say, what there should be some measure on W coming from the rest of the graph. We could just put some very arbitrary measure mu there, and say this will be the measure. And okay, essentially, if you do the same sort of analysis of what happens when you add or remove an edge, you'll get a sort of similar kind of inequality in each step of the interpolation. So you always get the log partition function is decreasing. I won't go through the calculations of that. And overall, this will again give you a sort of superadditivity that if you have the log partition function on the m vertex graph is bigger than the m minus n1 and the n vertex one, maybe minus some error. Okay, but I didn't want to. That wasn't the result I was most wanting to get. We could also, there was this. We put a measure mu on the vertices of W. So we said that there was some measure on this that was kind of coming from the rest of the graph, but I didn't specify what that was. And these inequalities hold uniformly in the choice of mu. And so what does that mean? Well, you get a bound on the partition function, an upper bound on the partition function for the n-vertex random deregular graph in terms of two graphs that are sort of both weighted by mu. So we have the vertices W here. We put some weight mu on them, and then the first term is what we get when we add essentially add in vertices and connect them up to the vertices of W. And the second term is what happens when we add edges between these vertices. So there's sort of a vertex term and an edge term. And whatever the original measure you had on W, you get an upper bound here. So you can take, so you can choose mu, and the sort of physics heuristics tell you what the right choice of mu to choose to get the best upper bound here. And so by doing that, you can calculate what the effect of either adding vertices or edges are, compute these terms, and you get you get an upper bound on the partition function. And in fact, if you choose the right choice of mu, you'll get the right upper bound on it. So the interpolation method also gives a way of giving sort of exact upper bounds to these quantities, and that's that's very useful to be able to do. So as long as you know the right heuristics for what the distribution should look like, you can get an upper bound of the right form. And so then the rest of the work is usually getting the right lower bound, and I guess that will be what I talk about tomorrow. Okay, so it's a good spot to end.
Other questions? No? Okay, so let's have 10 minutes for a coffee break, and then we have the second lecture there.